So for this section, we're going to be talking about some more advanced techniques in problem solving. Typically speaking, these advanced techniques are associated with conserved quantities. These are quantities that don't change over time. And having constant quantities can make your problem solving quite a bit easier. So the first one we're going to talk about for this particular module is momentum and its angular counterpart, angular momentum. In the next section, we're going to be talking about energy, which is far more useful, but we'll do momentum for right now. The idea behind momentum goes back to Newton's first law. If you don't mess with an object, it's just going to keep doing whatever it was doing before. We can actually quantify this using a quantity known as momentum, where momentum for any individual object is its mass multiplied by its velocity. Momentum here is a vector quantity. Now, the idea is when we're dealing with different systems, if there's no external forces present, the total momentum, so the vector addition of all the individual momentums, cannot change. Thus, total momentum is conserved. Only an external force can change this total momentum. So we can use this to solve problems without having to do or find intermediate variables, just by comparing their initial and final conditions. So here we have three molecules, 1, 2, and 3. Initially, they're all together, and they're all stationary. And stationary is by far the most important term. So this describes our initial situation, this first sentence here. We have three molecules. They all have different masses, which you can look by checking out further on in the problem. But initially, they're all together and stationary. So the trick to using momentum to solve your problem is to compare your initial and final cases. So we're going to start with the initial case. Now, we have three molecules here. They're all initially stationary. So to find the momentum of, say, number 1, we can take its mass and multiply it by its velocity. Right? So momentum is a vector because velocity is a vector. Now, in the initial case, we're told that nothing is moving. If nothing is moving, my velocity is 0. And what that means is my momentum is 0. And it's 0 in all directions. So if you want to be complete, you can put 0 into Cartesian form by having it just be 0 in both the x and y coordinates. It's up to you what you do. Now, for the second one, so for object number 2, it is also stationary. So by the same logic, it's also 0. And likewise for number 3, also stationary, also 0. Now, what that means is if we're trying to find the total or net momentum, doesn't matter what you want to call it, we need to perform the vector addition of all our individual momentums. And it will be 0. Now, you might ask, well, how does this help me solve this problem? Well, at the end of the day, we're asked to find the velocity of the third molecule. If momentum is a conserved quantity, because there are no external forces present, whether we're dealing with the initial or the final case, this momentum should not change. So the minute you have no external forces here, we're going to keep them the same. And typically speaking, if you do have external forces, there's not really a lot of point to using momentum, because at the end of the day, you would have to find the change in momentum using those forces, which is equivalent to finding the change in velocity using an acceleration. But when there's no external forces, it works real well. Now, with that being said, this here is the final state. I can actually use this idea of momentum to figure out this thing that I'm being asked to find, which is the velocity of the third molecule. The reason I can do this is I'm actually provided with the velocities of the first 2 particles. I can use those in combination with their masses to find their momentum. So that's what we're going to do. We're going to start with momentum number 1. Well, I keep wanting to put that as capital. We're going to find this by taking its mass. Again, I'm going to drop the units here, so we're working in masses of nanograms. Everything is consistent, and thus we will get velocities of centimeters per second out. So for momentum number 1, my mass is 150 nanograms, and my velocity is 10 along the x and 20 along the y. Again, momentum is a vector quantity here. You're best served by using some form of Cartesian notation. Now, with this being said, I can actually calculate this momentum explicitly. All I need to do is take 150 and multiply it by each of these quantities. So what this will give me in the x is 1500, and in the y I will have 3000. So that's the momentum of the first one. I can do the same thing for the second one. For the second one, my mass is 120 nanograms, and for my velocity, I have negative 15 in the x, or 15 to the left, and negative 8 in the y, or 8 down. I can then multiply these out to get my momentum for the second object. So when I multiply this out, 120 times negative 15 is negative 1800. That'll give me the x of my final momentum. And as for the y, 120 times negative 8 is negative 960. I can use this to find momentum 3, because at the end of the day, momentum 1 plus momentum 2 plus momentum 3 needs to equal to the net momentum. So what I can do here is I can make myself a little algebraic setup. Momentum number 1 plus momentum number 2 plus momentum number 3, which we're going to put in orange here. It has an x part and a y part. So let's just space these out so they line up. Altogether, these have to equal to 0. 0 on both the x and the y. Kind of like so. So with this, I can actually find momentum number 3, just by finding x and y here. If you do a quick little bit of algebra, again, how you do it is up to you. Momentum number 3 needs to be equal to 300 in the x, and in the y, we're going to need negative 2040. All right, and again, this is in, of course, nanograms, centimeters per second, because those were the units of my mass and velocity, respectively. Now, with this being said, I can actually use this to find the velocity of the third molecule, because momentum number 3 must be equal to the mass of the third one multiplied by the velocity of the third one. And I know here that the mass of number 3 in nanograms is 140. So I can put these two things together. I know what momentum 3 is, and I know it's equal to 140 times velocity number 3 to find velocity number 3. In other words, I can take this momentum number 3 and divide both sides by 100, or both components by 140. Right? And doing that will yield me my final velocity that I'm looking for directly. It'll of course be in centimeters per second, because I'm taking my momentum that was in nanograms multiplied by centimeters per second and dividing it by 140 nanograms. So this, what you'll see is this gives you a very quick way to solve problems involving things like velocities without having to worry about what the intermediate force is. And to do so, we take advantage of a conserved quantity, which is the total or net momentum. And the net momentum is always conserved in the absence of external forces. So even though there's a chemical reaction that takes place here, you'll notice it is explicitly stated that it is internal to the system. External forces can change this, but internal forces cannot change this total momentum.